The question of whether the universe is alive comes down to what we think life is. One of the primary features of nature is that living things are ultimately composed of non-living things. And so it is the organization of those things, the process by which they persist, and the information that they contain that determines whether they are alive. The simplest forms of life on Earth are viruses and bacteria, and these contain basic means of self-replication and consumption of nourishment. Prions, on the other hand, fragments of proteins, thus containing the same material as living things, also replicate, but they are judged not to be alive. The Encyclopedia Britannica provides definitions of life based on several considerations: growth, change, reproduction, active resistance to external perturbation, and evolution, but states that a conclusive definition is impossible. The universe certainly grows and changes, not only expanding but forming complex structures like galaxies, galaxy clusters, and webs of interlinked clusters. It may also evolve from other universes and produce spores for new ones via black holes. My own definition of life, explained here, is anything that can travel from one ordered state to another with a higher probability than a non-living thing. In other words, the primary definition of life is that which can keep itself alive. While this definition seems circular because it defines life based on non-life, it might be better to say that life and non-life cluster in distinct groupings, depending on their tendency to maintain an ordered state. A rock can stay in an ordered, intact state for billions of years if nothing external interferes with it. Therefore, another requirement for something to be alive is that it continues in an ordered state despite external interference. These definitions make it difficult to say whether the universe is alive, even if it is something akin to a fungus, because we cannot observe other universes, nor are we aware of any attempts to interfere with ours. In addition, we have no evidence that our universe reproduces, which would be an important characteristic for it to be alive. The universe does have an internal order that causes it to persist. Measurements of the expansion of the universe show that it is flat, meaning that it will not collapse back in on itself, nor will it rip apart. This means that it will persist indefinitely. Yet this could be no different than the rock. If nothing external interferes with the universe, there is no reason to think it wouldn't persist. Mathematically, however, it is possible to imagine what would happen if another universe were to interfere with ours. In a multiverse with many universes popping into existence, such as the theory of eternal inflation proposes, universes may collide with one another. One paper explores the possibility that our universe might be a bubble, and what would we see if another such bubble collided with ours? For example, the patch of sky where the collision occurred would show discontinuities with the rest of the sky. The appearance of such observations is discussed in this 2008 paper, where it is proposed that these collisions produce cosmic wakes, which look like symmetric disks in the cosmic microwave background, the earliest light we can see. What this means is that, although there is no conclusive evidence that other universes are interfering with ours, we do have theories about what those might look like. The next question then is, if our universe resists such collisions in some way, as a living thing might, how would it do that? If the universe does this very effectively, unfortunately we might see nothing at all because no collisions are observable. For example, if the universe is like a plant cell with the particle horizon, the furthest we can observe, being a cell wall, then we will observe nothing of these other universes. If, however, our universe has ways of repairing its walls after a collision, this might be present in the universe's DNA. That DNA would be roughly what we call the laws of physics. These are rules that the universe follows, which may not be the same from universe to universe. As mentioned in the 2008 paper, inflation, the rapid expansion of the early universe, limits the effects of bubble collisions. It also erases influence from the parent universe and creates most of the matter and energy in the universe at the same time. This doesn't necessarily mean that inflation evolved to produce those effects, but it is at least one mechanism by which interference from other universes is limited within our universe while allowing our universe to form. As Lee Smolin pointed out in a 2006 paper, eternal inflation is not mutually exclusive with his cosmic natural selection hypothesis for evolutionary universes from black holes. Therefore, there is no reason to believe that we could not have an entire ecosystem of universes that reproduce, evolve, and inflate from false vacua. Unfortunately, it is impossible to say conclusively whether the universe is alive without observing other universes. Whether our universe has simply been very effective at shielding us from those universes or whether they exist at all is unknown. We can, however, say that at one time human beings were in the same situation relative to planets outside our solar system, exoplanets. Indeed, we are old enough to remember when we didn't know whether other stars had planets. Now we can directly image them and in some cases determine some of their chemical composition. With new instruments such as the James Webb Telescope and gravitational wave detectors, there is no telling what the future will bring. The question remains that are we alone in the universe? What lies beyond the observable cosmos? And most intriguingly, is the universe itself a living entity, pulsing with the rhythms of creation and destruction? The universe is all of space and time and their contents. It comprises all of existence, any fundamental interaction, physical process and physical constant, and therefore all forms of matter and energy, and the structures they form from subatomic particles to entire galactic filaments. Space and time, according to the prevailing cosmological theory of the Big Bang, emerged together 13 billion years ago, and the universe has been expanding ever since. Today, the universe has expanded into an age and size that is physically only in parts observable as the observable universe, which is approximately 93 billion light-years in diameter at the present day, while the spatial size, if any, of the entire universe is unknown. Some of the earliest cosmological models of the universe were developed by ancient Greek and Indian philosophers and were geocentric, placing Earth at the center. Over the centuries, more precise astronomical observations led Nicholas Copernicus to develop the heliocentric model with the Sun at the center of the solar system. In developing the law of universal gravitation, Isaac Newton built upon Copernicus's work as well as Johannes Kepler's laws of planetary motion and observations by Tycho Brahe. Further observational improvements led to the realization that the Sun is one of a few 100 billion stars in the Milky Way, which is one of a few 100 billion galaxies in the observable universe. Many of the stars in a galaxy have planets. At the largest scale, galaxies are distributed uniformly and the same in all directions, meaning that the universe has neither an edge nor a center. At smaller scales, galaxies are distributed in clusters and superclusters which form immense filaments and voids in space, creating a vast, foam-like structure. Discoveries in the early 20th century have suggested that the universe had a beginning and has been expanding since then. According to the Big Bang theory, the energy and matter initially present have become less dense as the universe expanded. After an initial accelerated expansion called the inflationary epoch at around 1032 seconds, and the separation of the four known fundamental forces, the universe gradually cooled and continued to expand, allowing the first subatomic particles and simple atoms to form. Giant clouds of hydrogen and helium were gradually drawn to the places where matter was most dense, forming the first galaxies, stars, and everything else seen today. From studying the effects of gravity on both matter and light, it has been discovered that the universe contains much more matter than is accounted for by visible objects: stars, galaxies, nebulas, and interstellar gas. This unseen matter is known as dark matter, having come into existence alongside the rest of the physical universe before gradually gathering into a foam-like structure of filaments and voids, and allowing other forms of matter to form together into visible structures. The lambda CDM model is the most widely accepted model of the universe. It suggests that about 2% to 1. 2% of the mass and energy in the universe is dark energy, which is responsible for the acceleration of the expansion of the universe, and about 25% is dark matter. Ordinary baryonic matter is therefore only 4% of the physical universe. Stars, planets, and visible gas clouds only form about 6% of the ordinary matter. There are many competing hypotheses about the ultimate fate of the universe and about what, if anything, preceded the Big Bang, while other physicists and philosophers refuse to speculate, doubting that information about prior states will ever be accessible. Some physicists have suggested various multiverse hypotheses in which the universe might be one among many. In the vast expanse of space, we are but a tiny speck, yet our curiosity drives us to unravel our grand existence. Together we will venture into the unknown, guided by the light of discovery and the spirit of exploration.